So the previous models we made for covalent structures were the Lewis dot structures, but they don't really depict exactly where the atoms are going to be in a covalent bond. So instead, the actual structure and arrangement of atoms is through something called the Vesper theory or molecular geometry. So molecular geometry shows the 3D arrangement of atoms in any molecular substance. And it follows something called the Vesper theory, which stands for the valence shell electron pair repulsion theory, which says that any set of valence electrons that surrounds an atom is going to set itself as far apart as possible from any other atom. In order to do that, we have to maximize the repulsion so that the atoms can go anywhere around the atom. So remember, these are three-dimensional structures. Everything that's bonded is going to go as far away as possible. On page 78 of your notebook, we have a chart that shows the molecular geometry along with shapes and angles. If you haven't taken these notes, you can take them with me. If this is just a review, you can follow along. So the first type of molecular structure is called a linear structure, and it's when you have one atom and two things that are bonded to it, and no other lone pair of electrons that are around that central atom. The angle in between those would be 180 so that those outside atoms can be as far apart as possible. There would be two atoms bonded with no lone pairs. The second structure is called trigonal planar, and it's when three things are bonded to the central atom. There would be no lone pair of electrons, so just three bonding domains. Next is bent, and bent is when we would take a linear structure, but then that inner atom, the central atom, would have a lone pair of electrons on it. This would be like if we had nitrogen that has three bonding domains and then two lone pairs on it. Those lone pairs aren't going to bond anything because they're already paired up, and then you have two bonds on the outside, and it just bends that linear structure down. If you have four atoms, no lone pairs, that's going to create a structure called tetrahedral. Tetrahedral is like a cathedral that's going to stand up real tall, so it's the first of the three-dimensional structures that we have, so the thing that actually starts moving out into the X, Y, and Z axis. If we take one of those bonds off and put a lone pair on it, you get a structure called trigonal pyramidal. It's going to create a pyramid at the bottom and then the lone pair that sticks up at the top. A bent structure, so this is another type of bent, and it's if we take another one of those lone pairs off, or bonded pairs, and replace it with a lone pair, it's going to bend those two bonded domains down. So you would have two lone pairs, two bonded pairs. That's also called bent. Trigonal bipyramidal is when there are five bonding domains around a central atom. Octahedral is when there's six bonding domains, no lone pairs. If we take one of those from the five bonded domains off and make it into a lone pair, that's called seesaw, and it's seesaw because you have two at the bottom and then like that top that would seesaw over. If we still have five bonding domains, we replace two of them with a lone pair and one with, or three with a bonded pair. That's called a T-shape. So those lone pair of electrons, remember that they take a little bit more space around the atom than the bonded domain. So it's going to make these three that are left on there a full 90 degrees away from each other so that those lone pairs have the extra space that they need to exist in that cloud above the central atom. And then the last one is square pyramidal. It's where you have five central bonded domains and then one lone pair, and that one lone pair would go at the bottom. Again, it's going to take up more space than the bonded pairs would take up on here, so that's why it would create a square pyramidal. It's going to push all of those other bonds away. These are molecular geometry shapes. We also learned the electron geometry shapes, which aren't written on here. Electron geometry just goes off of the number of bonding domains around an atom. Whether there's a bond or a lone pair makes no difference. So anything that has only two things around it is called linear, and I'm going to circle the electron geometry names. So that would be linear. Anything with three things is going to be trigonal planar. So in electron geometry, we would call this, because there's a lone pair, two bonded pair, we would call that trigonal planar as well if we were looking at electron geometry. For molecular geometry, that's called bent. Anything with four domains is called tetrahedral. So that would be this shape. This has 4 domains, 3 bonded, 1 lone pair. So that would be tetrahedral for electron geometry. This is 2 lone pairs, 2 bonded pairs. 2 plus 2 is 4, so that's also a tetrahedral structure. Anything with 5 domains is called trigonal bipyramidal. So that would be here with seesaw, here with the T-shaped, and square pyramidal has 6. So these two, which both have 5, would also be called trigonal bipyramidal if we were looking at electron geometry. And then octahedral is anything that has 6 around it. So that would be this octahedral and square pyramidal. So I circled the ones that we would use for electron geometry. On page 79, we're going to look at hybridization. And hybridization is kind of the last part to the history of the atom and what we actually define as the atom today. So the Vesper theory is really good for predicting shapes, but it can't predict the relationship between the orbitals that we learned for electron configuration. So for example, if we were going to look at CH4, and we know that carbon's going to be in the center and it's going to bond 4 hydrogens. So we expect that our structure would look like this, and then we would say this is going to be tetrahedral. Well, if we look back at electron configuration, carbon's electron configuration would look like this. And based off of that, we would predict that we can only have 2 electrons that are bonded here, because these are the only 2 electrons here and here that can take another electron in. So it didn't make sense with electron configuration and where we expected that the electrons existed, and then what our predicted shape and Vesper theory would actually be, what the Lewis dot structure suggests the atom would be. So how can carbon bond 4 hydrogens when there's only 2 locations here? So this is where hybridization comes in, and it states that the highest energy level that you have, in this case is energy level 2, can morph together, and when it morphs together, it's going to create hybridization, or a hybrid orbital. So instead of us having a separate s and p orbital, this second energy level can just squish together and make an sp orbital. So this whole thing would be sp. And in the second energy level, we have 4 electrons. So we can just shift them all to an up electron. Now we have the spot for 4 electrons to come in, which is where the hydrogen electrons come and bond in that sp hybrid orbital. So this happens to anything that has both an s and p energy level that's actually making more bonds than we predicted that it could. When we denote a hybrid orbital for each of the molecular geometries from the previous page, we're going to use the s, p, d, and f orbitals that we learned in electron geometry and then just squish them together. So when we do that, the superscripts are going to equal the total number of orbitals that we're going to have to use. So like here, we had to use all 4 of the orbitals. The maximum s orbital that we could use was 1, because there was only 1 line from this s block. So the superscript on s would be 1. There were 3 total from p, so the maximum superscript would be 3. The d orbital has 5 lines, if you remember from electron configuration, and f orbital has 7 lines. So we can use any of these superscripts to equal to the number of lines that we would have had to use in electron configuration. The superscripts of the s, p, d all need to add up to the number of places that you have around your central atom. So this is where the electron configuration really does well for you. It allows you to know how many spaces around the atom are actually used. So when we look at the previous page, and I'm going to get my other notebook, when we're looking for hybridization, like for tetrahedral, there's 4 bonding domains, so we would say that this is an sp3 hybrid orbital. So there's 1 for the s, 3 for the p, 1 plus 3 is 4. for trigonoplanar, there's 3 bonding domains. So we would say S is 1, next letter would be P. We have to equal 3 because there's 3 bonding domains. So we're going to put a 2 there. That means that we used 1 S and 2 P orbitals to make this shape. This would be an SP orbital. There's 2 bonding domains, so 1 plus 1 is 2. There's 3 total domains around here, so that would be an sp2 hybrid orbital. So 1, 2, 3 total, superscript 1 plus 2 equals 3. 4 bonding domains around here, this would be an sp3 hybrid orbital. 4 bonding domains, sp3. This is 5 total domains. This would be an sp3, that gets us to 4, and then we add the letter D, that gets us to 5. So 1 plus 3 plus 1 is 5. This is 6 bonding domains. That would be an sp3D2. So 1 plus 3 plus 2 is 6. This is 5 total domains, so sp3, that gets us to 4, D, that gets us 1 more for a total of 5. This would be an sp3D, because we have to have 5 total domains. And then square pyramidal, we have to have a total of 6, so sp3D2, 1 plus 3 plus 2 is 6. Okay, and then the last page for this unit is about intermolecular forces. And intermolecular forces are the attractive forces between molecules. And this is what actually makes, like, those properties that we were talking about, ionic and covalent compound properties. This is what makes those properties sometimes not hold true, because in an ionic bond where you have a complete transfer of electrons, there's not attractive forces between outer molecules. In a molecule like water that has partial positive, partial negative ends, these partial positive ends can be attracted to a partial negative end of another water. So in order to break apart a bunch of water molecules, you have to break these attractive forces first, and these attractive forces are called intermolecular forces. The oxygen bonded to this hydrogen is called an intramolecular force. So when you include intermolecular forces, then you start getting higher boiling points, higher melting points, more energy needed to break apart a bond, just different interactions that you constantly have to break apart in order to, like, increase the temperature of something. This is why the boiling point of water is so high and has a high specific heat capacity, because of all these intermolecular forces that exist within there. There are 4 intermolecular attractions that we're going to learn. The first is a dipole-dipole. Dipole-dipole forces are forces between 2 polar molecules that one end is partial positive, the other end is partial negative, and it would be like an HCl bond. So you have a whole bunch of hydrochloric acid. This Cl would be partially negative. This hydrogen would be partially positive. If you have gazillions and gazillions of these in a system, this partial positive gets attracted to this partial negative, and that creates a dipole-dipole. So this molecule has a dipole, and this molecule has a dipole, and the dipoles are connected to each other. So that's called a dipole-dipole intermolecular force. There are times when you're going to have more than one type of molecule in a solution, and sometimes one of those molecules is going to be nonpolar, like a chlorine-chlorine bond. So neither of these chlorines is going to pull those electrons closer to it than anything else. And then you may add something like hydrochloric acid around here, where this is still partial positive, this is still partial negative. Now, because this partial positive is here, it's going to start shifting electrons this way. And when that happens, it's going to induce a dipole on a nonpolar molecule. So this ClCl, which didn't have any uneven distribution of charge, is now going to have an uneven distribution of charge, and it's going to create an induced dipole, which means that this is going to become partially negative and this is going to become partially positive. So it's going to induce that dipole. A hydrogen bond is the same exact thing as a dipole-dipole, only it's going to be between hydrogen and either oxygen, nitrogen, or fluorine. And the reason that these are so special is because oxygen, nitrogen, and fluorine have the highest electronegativity values. So when there is a bond between hydrogen and one of these three atoms, it creates a much stronger dipole-dipole force. And we had to denote a special name for that because it really changed melting points and boiling points of anything that has these properties in them. So same exact thing as up here, only now we're going to have something like water, which is partially negative, partially positive. This water that would be down here, partial negative, partial positive. This partial positive, partial negative attract each other, and this makes an extremely strong intermolecular force. So you would have to keep breaking these apart if you want to like boil this or change the phase of it. So really, really affects the boiling point and melting point, increases them drastically once you have something like a dipole-dipole or hydrogen bond there. And then the last one is a London dispersion, which is also called a van der Waals. These forces of attraction are extremely weak, and they are there all of the time in anything that exists. So matter all the time has to be able to attract to one another. So even if there's two nonpolar bonds right next to each other, there has to be an instantaneous dipole that takes place, and it's just atoms trying to figure out whether or not they want to make a bond with something else. If this force wasn't there, then nothing would ever go on to make a bond. So there's just a natural attraction between electrons and protons that exist no matter what, and that's called a London dispersion. They're extremely weak. They really don't affect anything because everything has them. So it's kind of like a negligible force. If everything has the same force, then it's like there is no force to it. So that's like what a London dispersion is. If we were going to order all of the forces of attraction that I taught you for chemistry class, ionic bonds would be the strongest, then polar covalent and nonpolar covalent. Hydrogen bonds are right underneath the covalent bonds, then dipole-dipole, induced dipole, and London dispersion. You are going to need to know the order of strength of bonds, so make sure that you know this order.